what is root? Well, for me, it's always important to emphasize that it's an open source project by the high energy physics community for the community. Here, the developers are right at CERN or at our partner institutes, and we are engaging with our user community on a daily basis. So if you have any questions about root and how to use it in particular for your problem, we also have a forum where you can ask your questions. So it's really a community effort, and at some point, who knows, maybe you might contribute yourself. Root was mainly developed really to drive the analysis at the LHC. So that was started in the 90s when the LHC was really planned. I think also Root started around that time, maybe late 90s. And of course, the example that we're the most proud of, that we show every time, is the analysis that led to the Higgs discovery in 2012. They were already done using Root. So for the Root was used for the plotting, the statistical analysis, and of course also for storing the data and processing the data. So I think this is quite familiar to you, maybe. Who has seen this plot already? Okay, yeah, already a few. So I think then after your summer student lectures, everyone will know it. This is the measurement of a Higgs boson decaying into 2 photons, and by the CMS experiment. And here you have the measurement of the Higgs mass and signal strength in both diphoton and 4-lepton channels by Atlas. So yeah, I mentioned that there are several things that Root can do, like plotting histograms. Here on this slide, I'll just give you an overview of what it can do. So not everything is relevant for today. Today we will mostly focus really on the basics that you need to get started doing some analysis with Root, right? So let's say your supervisor gives you a Root file with some n-tuple, so some data set that he wants you to analyze. By the end of today, the goal is that you're able to do this with the cutting edge classes of Root. But in case you wonder what Root can do besides like the final analysis steps, here's the overview. And some things we are proud of in particular is, for example, the C++ interpreter is quite powerful. So Root started as is actually not a Python library, so it's a C++ library. All of these parts of Root are implemented in C++ for performance reasons. And all of this C++ interpretation layer that allows us to also use it from Python is quite impressive. Then we have, besides functions for data storing and analysis and plotting, we also have some advanced libraries for statistical analysis. This RuFit, you might have heard about it if you're already working with these collaborations. Or for machine learning, we have TMVA. And then our newest product, so to speak, is our data frame that we use then for declaring your analysis and running it efficiently. And so I was mentioning there's a lot of data stored in Root files. Yeah, so Root is used to store data, like the data that was recorded by the experiments to discover the Higgs boson. And actually the impressive thing about Root's data storage system is that you can dump arbitrary C++ classes in a Root file and store whatever you want like this. Huh? And the experiments at the LHC, they use this to really store the output of their detectors at every stage of the analysis pipeline. Huh? So they have their own custom classes to represent hits in the detector. Then they save it into some raw format. That's how they usually call it in jargon. Then after they reconstruct their particles that the detector measures, they save like a list of leptons, jets, etc. Again, back in a new Root file. And then so there are between 1 and n further reduction steps. But at some point, you have reduced then your data to some digestible format that you can also store on your laptop and then do analysis with it. Yeah? So we will come we will come back to this again later when talking about our data frame, because our data frame and everything else that we show today is really targeted towards this final step of the analysis where you have your root files with some tabular data, and then you make plots out of it. Today, we will talk really about these final end-user data analysis, starting with histogramming, fitting. So fitting is a bit of a jargon for parameter estimation in high-energy physics, meaning we want to find, we have some hypothesis that depends on parameters, and we want to figure out what are the ones that match the data best. Then we talk about how you read data from root files, and then how you do a more complicated analysis with our data frame. And let's go to the Jupyter notebooks now. Let's get started by looking at histograms. So histograms is a very histogram is a very powerful tool to reduce data, right? So that's why we use it in high energy physics all the time. When you have measured millions of events, you don't always care about all the individual measurements. You want to aggregate them in some bins. You want to know how much measurements were between, in this case here, for example, 80 and 84 GeV or something. And so you just need some counts in the different ranges, or called bins, also called bins. And then do some statistical analysis with these bin counts. So, actually, this example of a histogram here is again from this Higgs discovery analysis. This time no, it's not the Higgs discovery analysis, it's later. Yeah, you see this here, square root of S 13 TeV. So this is from the LHC run 2, but nevertheless, same kind of analysis. So the Higgs decaying into 4 leptons. And all the histograms in root are represented by the C++ class, or to you it looks like a Python class when you are using root from Python. And the name of these classes always starts with a T. That's our convention in root. Then you have H for histogram. Then you have the number of dimensions in the histogram. So here 1. And then you have a data type for the axis of the histogram. So in this case, it's a one-dimensional histogram where the axis type is of type double. So like a real number, right? Represented by a computer. And another example would be TH2I, so two-dimensional histogram for integer observables. So now we actually run some code. So let's see how you would create a histogram in root and fill it with some toy data. So first you need to import root. Maybe I can zoom in a little bit. Can everyone read it also in the back? Is it large enough? Okay, nice, thanks. So let's import root and create our first histogram. So I will go through this constructor call here a little bit in detail, but then afterwards, the pattern is always the same. Yeah? Many root objects in their constructor, they accept first the name of the object. That should be unique because root is using this internally to identify the object. Then you have a title that is used mostly for visualization. And then for the histogram, you need to give the number of bins and the range. So, and then the final step here is we are sampling 5,000 random values from a Gaussian distribution and fill the histogram with it. So that takes some time because it's 5,000 data points. No, just it's actually the import that takes some time in the beginning, but then creating the histogram is rather fast. And if you want to know more about how to use the TH1 object, you can go to our reference guide. But usually you can also reach the same page by just Googling TH1 root, or sometimes it helps to say CERN root because root is quite ambiguous. So if you Google TH1 CERN root, you will probably land on the same page. So how do you draw the histogram, right? Now we didn't see anything. It's just an object that lives on the computer. but we can't really see it. So to draw anything, we are using here this JavaScript root backend. So this is an implementation of root plotting in JavaScript. So that means it runs natively on the browser, and then you can also interact with your plots. So this is what we recommend you to use when you are plotting your root histograms in the browser from a Jupyter notebook. You enable our JavaScript plotting backend with this magic command JSRoot, and then set it to on. And drawing always follows the same pattern. First, you create a canvas that you draw on. So this is of type T canvas. And then you draw the object on the canvas with this object.draw method. In this case, it's the histogram.draw. And then finally, you draw the canvas, and that's it. So this will always be the same thing also later on for graphs or other objects in root. So let's do it. And then you have a nice visualization of the histogram where you can also zoom. You can reset the axis by double-clicking on the surface, and you can also hover with the mouse over the histogram and read how many counts are there. Huh? Quite useful if your supervisor is looking over your shoulder and asking, so how many bins, how many counts are there again in this bin? So this is, it seems like a simple feature, but it's quite useful to quickly know how many counts you have in a given bin. Root functions. So I already mentioned it before. So we often compare hypotheses with data in histograms, and the hypothesis, we also want to represent it in sort of a kind of probability density function, for example. So we need a way to represent functions as well in the root world. And we do this with yet another class. So this time it's called TF for T function. And then you have the number of dimensions right after. So you don't need a data type because a function is just a mathematical relation. It doesn't store any data itself. So it's just TF, then the number of dimension. So as an example, let us now create a two-dimensional function that represents this sine x squared minus y squared function. So again, you give a name, you give a title, and then instead of number of bins, where you don't need that, a function is not binned, you just give the limits for the axes that are required. So two-dimensional function has two axes, x and y. And then to draw it, you follow the same pattern again. So you create a new canvas, you draw the object on the canvas, and you can also pass some drawing options in the string. You will find all the options in the reference guide. Here we are using this surf1 option to draw a surface plot in like the style number 1. I think if you use surface 2, it would look different. So in this case, we get here this surface plot that we can again interact with because it's JavaScript root. So you can really look at this function from all angles. Actually, I'm curious now how surface 2 would look like. It's a slightly different way of representing the surface, apparently. Nice. Huh? Okay. So how do we now bring the functions and the histograms together in a likelihood fit or a chi-square fit? Well, let's try to fit our histogram from before, the one with the Gaussian random numbers. So for this, we need to create a new one-dimensional function, a TF1. And now, this is really the most complicated part of this presentation, so bear with me here. I use a slightly more advanced feature in root to define this TF1 object. So what I want to do now is I want to define the function in C++. Let's say you have a complicated fitting function that you don't want to define in Python, but in C++ for performance reasons. Then you can actually write C++ in a Jupyter notebook with root. by just prefixing the cell, using this percent CPP magic at the beginning of the cell. So all the content of the cell thereafter is then sent to root's internal C++ interpreter. And then you have this function available in the root module as if it would have been part of root itself. So this is quite powerful. And it really allows you to benefit from the upsides of both C++ and Python in one script. So yeah, I really like to show this. And here we are defining this Gaussian function here that depends on some observables x. So you can think of this as the observable on the x-axis of the histogram. It's only one-dimensional, so we are only getting the 0th element of this array. And then this Gaussian is also depending on some parameters in this array par. And here we have two parameters, one overall scaling constant here, R0, and then the mean, R1. And you see that this Gaussian here is always has a standard deviation of 1. So it's a bit of a simplified version of the Gaussian. So just a Gaussian with the floating mean and normalization. So we define this now.
In the definition of the parameters, I see that you are indexing par and x as if there were arrays. But then in the typing, it says only double, as if it's not an array. So I'm a little bit confused.
Do we see this star here? Maybe. So this is how you declare arrays in C, actually. So yes, if it would be just double x, that would mean this function accepts a double. But if you have this double star x, it means it accepts an array of double of. So the length is not clear, but it's just basically a pointer to the place in memory where this array starts. And this is how you are passing around arrays in C++ as well. So it's like something that the language inherited from C. And now we can use it as if it would be part of the root module. So we use it in this case to instantiate this TF1 function object. Because what I've shown you before with the TF2 example was we are giving the mathematical expression for the function as a string. So in the second constructor argument. This time we're passing the C++ function that is basically wrapped by this root function object. So let's do this. And we get our own C++ function here from the root module. So everything that we declared to the root interpreter with this percent CPP magic, you can then get it from root like that. So we have now defined this fit function. And to do the fit, all that you need to do is you need to call th1, so the histogram dot fit. So here the th1 is called h, that was the one from the beginning. And then we call the fit method on it. And you pass the fit function. That should be a th1 object, sorry, a tf1 object in that case. And then you can also give some options to the fit, just like in the case of drawing. So there you pass some drawing options. Here you're passing fitting options. We only use one. We are using this S option here so that the fit function actually returns an object with a fit result. So S stands for save in this case, actually. It means save the result of the fit in this returned value here. Res for result. So it does that, and it also prints you the fit result on the screen. The actual parameter values, you see them here in the very bottom. So P0 and P1. For P1, this was the mean, right? We sampled the random values from a Gaussian distribution with mean 0. So if the fit value is more or less compatible with 0, that makes sense. So this is the case. So it's almost 0 within one standard deviation. So that's okay. And then the normalization constant, well, it's not exactly the number of events in the toy data set, because in the definition of the Gaussian, we didn't really care about about normalizing the PDF or any bin width or whatever. So that means this constant here is a bit random. So, but it is you can see it here. It's 500, and then you have some other information like how many iterations did the minimizer need to find the minimum. How far does it estimate it is away from the minimum? This is this EDM, estimated distance from the minimum. That's a bit technical, but what you maybe know from your physics classes is this chi-square quantity. So you see it here again in the fit result. And when you draw now the histogram after doing this fit, so again, the same way, create canvas, draw the histogram, draw the canvas, you see that the fit function is included in the visualization. And when you now hover with the mouse over the histogram, you will see not only the bin counts, but also the value of the function. So you can really compare things by eye, which is sometimes quite useful. You don't always want to rely on chi-square test statistics or something. Sometimes this can deceive you. It's always good to compare things by eye. Remember, it was a bit of a complicated way in which we were defining this Gaussian function, right? We were creating our own C++ function to define this Gaussian TF1. But I mean, since Gaussian distribution is so common in data analysis, there's also a built-in function in root. It's called Gauss. And then you can just fit your histogram to this built-in function, which is, by the way, the same function that we use to fill the random numbers. Huh? So you can think of it like there are some TF1 objects that always live in the root module, no matter if you created them or not. And you can reference them by using these names in a string. So for the full list of the supported built-in functions, you can follow this link. But here we're using the Gaussian. And we get the same result as before, at least for the mean. For the constant, we now get something else because it's the normalization is a bit different in the built-in Gaussian. And then we also have now an estimate for the standard deviation, which is compatible with 1. So that matches again the Gaussian with mean 0 and standard deviation 1 that we use to fill the histogram with. So if we now draw the histogram, you see here the same result as before, because now we just use the built-in Gaussian instead of our custom one. But of course, the end result is the same. Once your fit becomes more complicated, like in the case of these LHC Higgs combination analysis, yeah, then you don't only fit one histogram at a time. Then you start to fit like 50 or even 100 histograms, because then each analysis group, they measure their own decay channel or their own observable. And then you want to do some combined measurement where you are then fitting all these histograms with a common hypothesis that has like a global hypothesis on the Higgs mass, for example. So you start to have a very large likelihood function. And to actually find the minimum, you need to take care that this likelihood function is implemented in a very efficient way so that the minimizer can evaluate it very, very often. And we have a library inside root that you can use to implement these very efficient probability density functions and likelihoods. It's called RuFit. You will maybe use it when you are working with CMS or Atlas or any of the big LHC experiments in your time as a summer student. Okay, we can also visualize graphs in root. Not surprisingly, this is quite a common thing to do. So just a set of points on the X and Y axis. And the class that allows you to do that is called the T-graph. And I just give you one example how to use it so that you have seen it at least once, but it's quite intuitive, right? So in this case, the T-graph doesn't even take a name or a title as a constructor argument. In this case, we are just filling the t-graph with a set of points from a parabola. So here we have, so in this loop between 20 and minus 20 and 21. So actually that means from minus 20 to 20 inclusive, we are filling the points, the graph with x and minus x squared. And then to draw the graph, you can do the same thing. In this example, we're actually using some member functions of the graph to define the style. So here, the marker style, the color of the line when you draw it, and the title. It looks like this in the end. It's not very surprising. So you see here these points on the parabola that we were filling the graph with. And again, since it's JavaScript root, you can hover over the points and see their x and y values. So just to show you an example for different drawing options. So here is another one. If you draw a graph on a canvas with this tgraph.draw, you can also say, hey, draw it in this bar plot style. So that's what the B stands for. The A stands for redraw the axis. Well, this is, by the way, I think the default behavior anyway. And then the B stands for bar plot. And again, the one is just the first kind of bar plot style that root has built in. And then you have a bar plot instead of a regular scatter plot with points connected by a line. So these were some basic plotting examples, but what I really like to show you now is some examples for plots that are very common in high energy physics and sometimes difficult to implement with other tools. Yeah? So like here, we see here this histogram stack, for example. You have here some points with the observed data here in black. But what the Higgs analysis here in the 4-lepton channel did is they didn't compare the data to some function like we did with our TF1 toy analysis, but you were actually comparing the data to simulation. So to simulated data that is then also represented in a histogram. And to visually distinguish them, we are often representing the actual data in these black dots with error bars. And then the prediction, so the simulated data for a given Higgs mass hypothesis in this example, we are representing this in this shaded areas. So these are also histograms, TH1s, so the blue one here for this diboson background and the red one for the Higgs boson signal. So these are then also histograms filled with Monte Carlo predictions. And you see that you have different components of this Monte Carlo prediction. So you have this the signal component here in red, the background, diboson background in blue, and then some other background in purple. And you want to stack these on top of each other in your canvas to represent the full expectation for this measurement. We have a class in Root, it's called the TH stack. And you create a TH stack from a list of histograms. And then when you draw the histogram stack, so if you call it TH stack.draw, it will give you something that looks very similar already to this kind of plots that I showed you in the beginning with the data to Monte Carlo comparisons. So what we are doing here is we are creating an array of actually 3 TH1Ds, one-dimensional histograms. Then, okay, we set some title here and we create this TH stack object here. And then in a loop, we are filling these individual histograms with random numbers. So in between these random number filling, I'm changing the mean of the Gaussian of this function that I sampled from, just so that the 3 histograms are not the same, right? And then also the color is different for the 3 histograms. And then the histogram is added to this stack. And in the end, we draw the stack. And that's what you see then here in the output of this cell. And when you hover over the bins again, you see actually the bin counts for each histogram in the stack, as if you would have drawn them individually. So another example for a high energy physics specific use case is here these efficiency curves. So this is maybe requires some explanation. So what do we mean by efficiency curve? So often you have an analysis where you are doing some filtering. So let's say you have a mass spectrum of some 4-lepton resonance, like we use in this Higgs analysis that I just showed, and you want to filter some your events according to some criteria, like events that only have well identified leptons, or events with a certain mass range. So then you want to see, okay, how many events are in my histogram before and after the filter, so that you can compare, okay, how much of the signal survived the filters, how much of the background is still left, to do these kind of studies. So filtering is very, very much essential for high energy physics analysis. And by filter efficiency, I just mean the rate of events that survive the filter. So often when you do an analysis, you want to find filters where 100% of the signal events survive, and fortunately 0% background events. But that's usually never the case. So you have to make a compromise. And for this reason, it's important to study these filtering efficiencies. So I'll show you here an example on how you could do that. Let's say you have two histograms. One histogram with the events before the filtering, and one right after. So this H pass for the passing events, and then total for the total events before the filtering. So in this example, I just set up random Gaussian data sets again. So let me just plot them. It's easier to talk about it then. So here I for both the passing histogram in red and the total histogram in blue, I just sampled them from a Gaussian distribution. So, but let's pretend this is really, you got to do this histogram by doing some proper analysis of a selection, right? And then you want to know what are the filtering efficiencies in each bin. So for each bin, how much events of the blue histogram are still left in the red one. And this is quite easy in general, because it's just, you need to divide the one histogram over the other, and then you have the ratio. But the problem is, when your professor then comes and asks you, hey, you told me this efficiency ratio here, but I have no idea what the uncertainty is, and please add the error bars to your efficiency plot. Then, okay, so what do? You think about your Gaussian error propagation that you did in the physics lab, and then you realize that you might get the wrong results with this, because inefficiency is by definition between 0 and 1. And if you do Gaussian error propagation, then this is not considered. So you might have error bars in the end that extend above 1 or below 0. So your professor comes back to you and tells you, hey, I don't trust in your results. It looks unphysical. So then you actually have to do some Bayesian error estimation, where you consider, like in a prior, that your efficiency is between 0 and 1. And that's quite complicated. And this T efficiency class takes care of it for you. That's really the message here, so that you don't need to do this complicated error propagation yourself. So that's why if you then create this T efficiency here with from the passing and failing histogram, and then draw it, then you will see it automatically comes with the error bars that are using this correct uncertainty estimation for efficiencies. This exercise is very similar to what I showed you in the presentation. So you're defining a model function in C++ and fit it to a histogram. The difference is that the histogram is not filled with random numbers, but this time it's filled from a Python list. And the function is not a simple C++ function with only one function body, but it's actually a function that calls two other functions. So we have here one for the background, one for the signal peak. They are defined individually just before, and then you get this total fit function here. And so in the end, once you fit the function to the data with the similar commands to what we saw before in the lecture, it should look like this. So that's the expected results of the exercise. You have some detailed instructions here, and the solution is also at the bottom. I encourage you not to look at it until you have really done it yourself. Let's look at the solution together very quickly. So, so for the fit function, it's like in this example with the custom Gaussian from the lecture. So you pass here the C++ function via the root module. Then you give the minimum of x and y. Sorry, of x and the number of parameters, which is 4. So this is probably the most complicated part because you need to infer the number of parameters from reading here the function definition. So here you know that, so here the background, it uses par 0, 1, and 2. So that one has 3 already. The peak uses par 0, and that's it. So that means 3 plus 1, in total 4 parameter. And this information needs to be known by the TF1 object so that it can internally create the arrays of parameters with the right size. Okay, so then and then you fit here the function to the histogram. Here there's also a little gotcha that tripped me up at some point. Yeah, so you get here this error message, but it tells you what to do, right? So you can use this save option. So that's this warning doesn't happen. And then for drawing, the new information that you needed was here, this E option. So capital E is the drawing option for drawing histogram with error bars. So you might either find this in the documentation for drawing histograms, or just if you Google CERN root how to draw error bars, it will probably show you. Oh, and that's a general advice. Root is not the most Googleable name for a software framework, because root might also mean other things with computers, the super user or just the tree. So if you Google for something root related, it's good to ask for CERN root. And so that's the advice.
The root files are really what's at the core of doing an analysis, because this is where you read the data from, and potentially also where you read your data or the results of your analysis back to be able to reuse or to reinterpret. The cool thing about these root files is really that you can write any object to the files. So a root file, we refer to it as a T file. So again, the T at the beginning. And that's really the kind of the object that you use to interact with when you're running root or when you're doing your analysis in a notebook. So the files, they're kind of special. It's not like you can open them in a text editor and see what's in there. They're binary files. And the reason behind this is that we can apply compression and all kinds of trickery to make sure that the files are as small and as optimal as need be, because, well, as you saw, we have 2 exabytes of data, so we kind of have to think about how we store it. You cannot just write them down. We talk about root files, but really what's inside of them is kind of like a hierarchy. And if you use your terminal and you print, for example, what's in a directory, you see that there are maybe subdirectories and files. Root files kind of have the same feeling, where you can have directories inside the root files or objects that are kind of hierarchical. How to use and how to interact with a root file. Let's start with just importing root as usual. This is always how we start. Let's wait for it to finish importing. There we are. And now the T file. So in this situation, we want to create a T file from scratch. So we don't have any data yet, but we want to write some results to a new file, or well, to see how it works. So to create a T file, kind of similar to what you saw with TF1 and all kinds of root functions, really you just create a file by calling root.tfile, and it takes two arguments. The first one is actually the name of your file, and the extension we use is .root. So anytime you find a file that has .root, you know, you can be fairly certain that it's a root file. And then the second parameter is kind of the mode or the option you give to the T-file constructor, and it kind of basically tells root or the T-file creator what you want to do with the file, and it kind of describes the policies on how you want to handle the file. So in this case, I said recreate, which means that I tell root that, okay, even if the file already exists, I don't care what's in it, just remove everything and let me start from scratch. This can be a bit of a dangerous option. So if you only want to read, what I recommend, or what we recommend, is to not give any option. Then it will always use the default read option, which means it's read only, so you cannot modify it. So yeah, when you're handling data, that would be the recommended way of doing it. And then if you're done with your file, if you're done writing it or reading it or whatever you want to do with it, you want to close it. So you can close it again by calling fclose. Good to note here is that in case your program terminates, or if the object we call f is destroyed, the file is closed automatically. So in most cases, you don't have to actively do this. Another nice thing, especially because now we're using Python, I don't know, who has ever opened a file in Python using the with, then you have like the file name, whatever. Yeah, I see a couple of hands. Good. We can do exactly the same thing here. So we have with root tfile and then exactly the same constructor as my file. You can do something with the file inside the scope, and then you will see that once you exit the scope, the file gets properly closed and you don't need to worry about it. Suppose we want to get the size of the file, we can say my file dot, or I actually want to print it. File dot size. And we can see that the file currently has 220 bytes already, which is the metadata that gets created when you create a T file. But there's no content yet. Okay. The content is what we are going to do now. So with the following example, I kind of want to walk you through how you can write actually an object inside of the file. So we have our context manager. We create a T file. This time we call it f. We create a histogram, similar to what you did in the previous part of the session. Just has some, but still actually an empty histogram, and we call it h. And to write this object, h, into the file, we can call write object on the file with where we specify the actual object and then the name of the object. So we say h and h.getName because we already gave h a name, which is my histo. And then we can call it, and it doesn't really output anything, but we can check actually that it wrote it in bit. So as you see here, the argument of the th1d is the name of the histogram, which Jan has already explained is kind of the common pattern where you give a name to the object. And good to note here is that this name is actually also what we use to identify the objects in the file. So even though in our Python program we called it h, if we want to then read it back from file in a different program, it's not called h, it will be called myhisto. So that's maybe a good thing to note. Okay, so now we should have a file, or we already saw that we have a file called myfile.root, but we want to check whether actually it contains the objects that we just wrote. And let's first just try with bash. I'm sure, I hope that everyone's familiar with the ls command. And we can see indeed that there is a file called myfile.root. It's also larger than what we saw before. It has more bytes. So there's something written to it, which is already a bit reassuring. But now, if we want to actually check if it contains the histogram we just created, we also provide a special command called root ls. that will actually show you the commands within a root file. So if you have a root file and you only know the file name, but you aren't really sure what's in there, you can use root ls to inspect actually the contents of the file. So to see it in action, yeah, exactly. So we call root ls with exactly the same commands, -l with the file name, and it shows you that we have a th1d written on 14th of June with a histogram called myhisto, and actually it also contains the title. Now, this is all fine. You have the file, you know how to show it in Bash. But of course, you also want to be able to interact with it because you create a histogram, you write it out, but then you want to fill it or maybe plot it, or I don't know. You want to programmatically interact with it. We can do it again by using tfile. So now we open again with the context manager. We open the file. Notice that I don't give an argument right now because I don't want to recreate. I don't want to update. I just want to read, which will be the default. And then I can on the file object I can call get with again the name of the histogram we just created. So let's see what it does. Exactly. So now we open the file, we get it, and we can verify here that we have a histogram called myhisto with 100 bins, which is exactly what we created. So that's files in general. Now let's move a bit into what's usually in these files, which are HEP data sets. Because I don't know what your background is, just to make sure we're on the same page. A high energy physics data set typically contains many, we're talking about a couple of million per file, of statistically independent collision events. Maybe the naive solution would be to create an object with my event and then have multiple of them and read them back. However, that's very inefficient because every event has hundreds to sometimes thousands of data fields. And if you need to read back every data field every time, yeah, you might need a lot of coffee breaks before your analysis is finished. So instead, we thought about how we can store this efficiently. And so we came up with a dataset specification that it's columnar. So a dataset, we organize it in different columns, and these columns can store elements of any C++ type. So it's fundamental types like integers, floats. You can use collections, so vectors, maps, arrays, or you can even provide your own classes. So if you have a class, myElectron, you could write an object of myElectron into a dataset. And to kind of show you what it looks like from a very, very high level point of view. So the green part here is an event or an entry. And then this entry is split up into columns, or typically we also refer to it as branches. And it can be anything, like can be a number, it can be an object. And kind of a way to also think about it is a high performance Excel sheet. So you have really this tabular view on your data. And this data set, we call it T-tree, or that's the name of the class. We use it again, so it's a tree with the T in front of it. And it can be written to a T file just as any other C++ object or root object, as we just saw. And the nice thing about this format is that you can read columns independently, which is very nice if you have a massive data set of maybe 1,000 fields or branches or columns or whatever you want to call it, and you really only need 2 or 3. It wouldn't make any sense to read everything, but with this way you can really optimize the I/O, so the reading and writing from disk performance, especially with respect to other dataset formats that already exist. I'm going to show you what a T-tree looks like. We again used, so now this example file already existed. You can find it in the repository as well. If we call root ls on this example file, you'll see that we will have a T-tree called dataset, and we can interact with this. We now know that we have a T file with my dataset, and we want to be able to actually analyze the data that's inside of it. The recommended way is nowadays roots are data frame. And here is also where I kind of will contradict what Jonas said in the beginning, that every root class is prepended with a T. This is actually not fully true, because the modern classes and interfaces we have will actually start with an R, which also logically maybe makes more sense. So if you have the choice between using an R interface or a T interface, I would recommend using the interface that starts with an R, because it's the latest and greatest. Okay, so in our case, now we're talking about roots are data frame, and it's really the high level analysis interface. So if you're doing physics analysis, is really what we recommend you to use. It's very nice to define the steps that you have to take for your analysis, the sequence of operations, and then under the hood, our data frame takes care of making sure that everything is optimized and runs as fast as it can run. So with root R data frame, you can provide different sources. You don't only need to read from root files, it's the most common way, but you can actually also create an R data frame from a CSV file or from a NumPy array, which we'll see in a bit. And then you provide your steps. So that could be a filter, it could be a definition of a new column, it could be anything. And then you output it to a histogram, to new root files that you can use, then perform your fits, or really any user-defined operation. Just to summarize, our data frame really allows for writing and actually also reading and actually also writing trees. And really our goal is to make life easy for you. So how it works in action. As with the other root interfaces, what you do to open is you need the name of your tree or the name of your data set in general, and then the path to this data set. This can be a path on your local machine. It can also be a URL to a file that's hosted somewhere else. And then to create our data frame, simply we call root.ourDataFrame with the name of the data set and the path to the data set. And pretty much that's it. So to see it in action, again, we have to import root and we open it. And yeah, exactly. So we have the data frame, and you can see that we have 4 columns, A, B, vec1, and vec2, which we now can actually start using to define our analysis. Let's call it for now. So we can define new quantities, which means with that, so we started with 4 columns, and using define, we can actually add more columns, also using the data that's already in the file. We can filter rows according to some conditions. For example, if you have the column A, and you only want the entries for which the value of A is larger or smaller than a certain amount, and we can do some data aggregations. So to see it in action, for example, in the define, we want an additional property called C, which is derived from the columns that we already have A and B. So we can call dataframe.define and really just give the expression on the names of the columns. So we don't have to know exactly what's in the columns, only have to know that it's a numerical value. Then we can actually define a filter on this new property C. So we're only interested in the entries in the data frame that have C smaller than a half. We can count the number of elements that are left in our set. We can get the mean, and then we display the values that we have. So see it in action. So we can see that after we have performed our filter, we're left with 111 events, and the mean of our column C is 0.39. And we can actually show the first n entries. By default, is 5 entries of the data set, just to quickly verify, what it looks like. And we can see that's actually correct. We did the addition right. Okay, so that's really our data frame in a nutshell. Of course, now you also want to do, or once you've executed your analysis, you've defined your filters, your calculations. You want to see your results, and of course, Jonas already showed how it works with histograms and with functions. But our data frame really also can help you to streamline the creation of histograms and graphs and any way to show your results. So for example, and again, we used Geo's root again, it looks very similar to what you already saw. We have to create a canvas, but now what we do differently is we already have the data frame, and really only what we need to do, if for example, we want to create a histogram showing the results of the contents of vec1, is call data frame histo1d, and then the name of the column we want to create the histogram for. And then we can draw it and draw the canvas as usual. We get a nice histogram, and even though, so as you might already guess from the name, VEC1 is actually not flat data, but it's entries containing vectors that maybe are different sizes for every entry. RDF really is able to nicely like merge it together into one concise data frame without you having to think too much about it. But you can think about it if you want. And just to kind of give an overview, so histo1d will create a one-dimensional histogram, so the one we already saw. And then we also have functions for 2- and 3-dimensional. And it's as easy as providing just only the column name, but you can also actually provide more parameters in the form of a tuple that you can pass, that you already saw in the that's called vanilla histogram function. So the number of bins, min, the max. We can give the histogram a name, we can give it a title, we can say the number of bins, the x low, the x up, and then put it all in a tuple and give it to the histo1d function. And then if we execute it, you'll actually see, so it's the same data that we saw in the previous histogram, but now with these parameters, we actually can kind of control what parts are visible in the histogram. And I have some points that are maybe good for you to take home, really, if you start using our data frame and analysis in general. So RDF is really built with a flexible workflow in mind. And the most important part is that you think really about how your data flows through the workflow. So if you have certain properties, really the important thing is to think about which parts do I need to filter, which parts do I need to define, and yeah, how does it kind of look if I draw it out as a kind of like a graph, which RDF can also do for you. What really does it look like from a bird's eye point of view? And then, of course, you can also, once you have this data flow, apply actions to it, so such as creating the histogram. A really important note here is I mentioned that under the hood, our data frame does a lot of optimizations and makes sure that the analysis can be run as fast as possible. And there's one task that's kind of left as a responsibility to you, to the user, and that is to make sure that all the transformations and actions, so creating the filters, creating the defines, saying that you would like to create a histogram, it's really important that you kind of write this down, like define this in your code before you do actually anything with the results. And the reason is that our data frame has this notion of laziness, which means that first we schedule what needs to happen, and then only if you want to access the results, the execution happens. So if you already access the results and then start amending to it, kind of the whole notion of this laziness is removed. So really only, try to be as lazy as possible. That would be, and then really only after that, look at your results. So we have our data set and we want to create 3 histograms, one for A, one for B, one for VEC1. Now, if you create the histogram and then get the value from the histogram or plot the histogram after each definition of the histogram, the data set will get processed 3 times, which is not ideal because ideally you just want to process the data set once and then only access the results. So here, and the reason why it happened here is because you call histo1d, then get value, which will actually run the workflow, and then you do it again twice. Now, to do it correctly, we would go the other way. We first define all of our histograms, and then only after that you will get value, and you can see that the data set is only processed once. I just want to give a summary on the type of operations that we have in RDF, and there are 3 main types of operations. So the first one is transformations, and that's really the category of filters, defines, and there's also one called alias, which really lets you define, or the thing what it does is it lets you kind of rename certain columns. And there's a bunch more that you can find in the documentation. So it really modifies the actual data frame that you're using for your processing. Then the second one is actions, which you can use to aggregate parts or maybe even the entire data set into a result. So for example, creating a histogram or counting the number of events processed, getting the mean, getting the min, getting the max. And then we have a third one, which is queries, which are actually not being put into the workflow. They're really kind of for you to get information about your data frame. So for example, what are the names of the columns I have in the data set? yeah, what are the types? You can actually, and then save graphs. If you have your nice workflow, you can actually create a visualization of what it looks like, just for you to visually verify that all the filters are in the right place. And yeah, just to check. Your task or your challenge or exercise is to find the hidden normal distribution. So really what you have to do is use our data frame to define the filters, find the defines, and then find the hidden distribution by the natural logarithm. There are two links. The first one is the R data frame class reference, and it really shows you the name of the functions and the type of I can actually show you. It will show you exactly all the functions you can call. It has a really nice cheat sheet that's divided according to the three categories that I explained earlier. So we have the transformations, the actions, and then the queries. And this is really a perfect starting point for using RDF. If you want to do something but aren't really sure what it's called, you can just go here. Say, for example, you need to define a filter. You can click on here and it will bring you to actually the interface and it will tell you exactly what the arguments are you need. One thing to note is that this is the documentation is for C++, but you can pretty much one-on-one also use it for Python. And then the second one has some tutorials, both in C++ and Python, and you can use it as an example and maybe see if you can mix and match some of the things for your solution.
The first step that we need to do is to create the data set, which we know how to do with the data set name that we were told and the root file. And the second step, which we can actually do in just one line, consists of a few sub-steps. So I'm pretty sure that most of you got to the filtering part, so that the b has to be less or equal than 0.5. And then the second part that was maybe slightly more tricky is to define this logarithm of a. And here we're using the root tmath class, which gives you the log a. So this is the second step. And then we were told that if we look into the distribution of this new column that we called log a, we should get the normal distribution. And now we can just use the jsroot command. Now we can just do the drawing. So the root t canvas, and we draw the histograms, and then we draw the canvas. And what we obtain is indeed something that looks like the normal distribution.
We are going to discuss now something which is very, very common for high energy physics analysts, which is the fact that we have to most often work with the collections in our data sets. So you will have, since the data sets often represent physical quantities of particles that collided in an event or that resulted as a collision, you will have more than one element in the same row. So that is why you have collections. In our data frame, you have certain specificities. For example, you will see here and there something that is called root rvec popping up. This is just the in-memory representation of a vector of particle properties that we have in root. So nothing weird about it. It's just our own way of representing it, but you can just visualize it as a vector in mind. And other than that, now we will take a look at the first example here. Let me zoom out and then we start. So we have our usual constructor for the R data frame object. This time, if this is still visible, I hope, this time we have a different data set, a different file. And in this data set, we have 4 columns with the following names that you can see here. And now we would like to inspect the data sets. And in particular here, I will use a functionality available in our data frame, which is already a bit more advanced, which is the possibility to convert one or more columns of your data set into NumPy arrays. And in this case, let me just start with one column, the column E. If you call these as NumPy object method here, you will get a dictionary of NumPy arrays where the key is the name of the column and the value is the NumPy array representing the values in the column. And I'm simply, in this cell, I am printing one by one all the elements of this particular column, row per row. So in every row, we have three in particular, row 0, row 1, and row 2. I wanted to print it out explicitly to screen to show you the fact that not only we have collections inside of the column, but we also have that every row has a different size of the collection. And you have to keep this in mind because it makes things a bit harder to manipulate and process, right, in your data analysis pipelines. So now comes really the important bit of this part of the lecture, and I will take some time to discuss what's happening here. Here we are for the first time trying to do something to process somehow the data set that contains collections. And we want to perform an operation that has both the aspect of creating a new observable, but at the same time, we are also performing a selection. Let's take it step by step. In the expression that you can see highlighted in the middle of the slide, there are three variables, three observables, px, py, and e. These are the columns of our data set. And then we are doing some manipulation here. From left to right, we have an external call to a square root operation with an argument. And then right after the square root operation, we have this brackets with square brackets syntax. Now, the square bracket syntax is exactly the same as a NumPy square bracket syntax. What we are doing here is we are masking the outer array with the elements from the condition, the criterion present within the square brackets. So let's take a look at that for a second. We have e greater than 100. You can guess what this does. It checks for every value of the NumPy array of the array at the current event of the column e, whether that value is greater or not than 100. So the output of e greater than 100 is not just one Boolean, like one true or false. It's a collection of Booleans, one per each element from the array e, right? And this is how then the outer array, so the result of the square root, will be masked. So whatever comes out of the square root operation on the left will be another array, but then we select from that array only the elements that pass the selection criterion e greater than 100. And okay, so now we can then go to the square root operations. In particular, the parameters here, as I said before, they are collections. So we are in the current event, we have px and py. They represent the collections of px and py for the particles in the event. And you see that we are performing some manipulations here. We are multiplying them, we are summing them, and then there's their square root. The important bit to remember here is that the dimensionality of the arrays is always preserved. What do I mean by this? Px times px is a scalar product between the two vectors. So you will have the same dimension coming out of the operation. The sum is again preserving the dimensionality. So if px and py have size 3, then the sum of them will be still a size 3 vector with the elements summed, element by element. And then the square root, same thing. So in general, we are preserving the dimensionality of the input arrays. And then finally, the whole expression is give me the square root of the sum of squares of the two vectors, and then select only the elements that pass the criterion. I said that we are doing a selection, right? Because there's this masking operation with the array greater than 100. So when I say selection, it kind of, you could think about it as filtering your data as a cut in your analysis workflow. But there is an important distinction here. The distinction is between inter-event selection and intra-event selection. So the first category is whenever you have a question, a query, which output should be true or false. So for example, give me all the events where the number of muons is greater than 2. For every event, you check how many muons do I have? Is it greater than 2 or not? And this, if it's false, it means that you do not want to see that event at all for the rest of your analysis. You don't care about it, so you discard it. Operations that discard an entire event, these are properly called filters or cuts. And in our data frame, you use the filter operation that we have seen before for this type of filtering. In this case, we are doing a filter, but we are not logically discarding the entire event. We are saying, okay, within this event, I want to keep some of the particles, those that respect a certain criterion. So in this case, we are still interested in seeing the event afterwards, just slightly modified. So this is why in this example, you see the define operation being called and not the filter operation. This is an important distinction and kind of the main point when processing array data with our data frame. Okay, so the question is, here in this particular example, we are using the square root function. And why don't we need to prefix any namespace to the square root function? Well, in this case, the square root function comes from the standard C++ namespace. So this is std square root. The way the C++ programming language works is if the function arguments, in this case, px, py, these are of type rvec. If the function arguments match with the signature of the square root function that has that type, so root rvec, then the compiler, the program will execute the correct function even without you having to explicitly write the namespace. And in this case, it's not ambiguous because there is not another square root function at the global namespace, let's say. So the compiler knows what to do. And this in particular is also different from the tmath : square root function. So there's no ambiguity there. Of course, yeah. Here instead you can give tmath square root, or you can define your own square root function and use that. The only requirement is that it can be interpreted by our C++ interpreter. Yes, for now at least. Now we have this new column, good PT, and we can try to plot it with the usual histo1d operations that we have seen already many times now. And it should be visible here, yes. So now we have this histogram that is being plotted, only keeping the elements, the values of the PT of each event that passed the selection process in the previous slide. It's going to be an exercise on the same subject. So we have the data set that we used in the previous exercise, and we know that this data set contains two vector columns, vec1 and vec2. We have a mixture of Gaussians and some background noise in the vec1 column, and then there is an assignment to remove this noise in order to plot the Gaussian peaks. In order to do that, you can select the elements of vec1, the column vec1, for which the square of the corresponding elements in vec2 is less than 0.1. So the exercise is to perform this selection process in order to then plot the histogram of vec1 that shows this the two Gaussian peaks. So again, the assignment was to find the peaks of Gaussians that were hidden in this data set. Let's quickly open our data frame object. So we have the data set from example file.root. And then we're interested in columns vec1 and vec2. we have to do this task of removing the background noise by selecting the elements of vec1 for which the square of the corresponding elements in vec2 is less than 0.1. So we have this objective of doing a selection intra-event within the same event by event then clearly. So we have to create a new column in this case. It's going to be good particles. And here what we do is we call define with the name of this column. And what is the selection that we have to perform? So we want the elements of vec1 in the end. So vec1 is going to be our output vector. And then we can do the square bracket selection like with an NumPy array. And in this case, the selection criterion is the square of the corresponding elements in vec2 is less than 0.1. So you see, even though we are performing a selection, it is indeed a case where we want to create a new column just to store the values of the correct particles that pass the selection. And then we can use our good old trusty histo1d operation on this new column. And then we do the plotting. So canvas, and then see the draw. Let's see if everything went according to plan. Something didn't go according to plan.
Data.
Sorry? Data. Yes. Good. So, okay, we open the data set, we create this selection, and then we see the histogram being plotted. So you have the two peaks. You could have also decided to plot vec1 just to check. And if we do that, see that there was this extra noise in the original column that we removed by creating the good particles column. Was anybody successful in this exercise? Just as a show of raise of hands? Okay. It's one of the more advanced concepts here in the dataset manipulation step. So try to take some time really to make it yours. How to save a dataset once you are done processing it. You remember from the slides that Florina was discussing that we have this concept of the root file, so the T file, and that we can store anything in it. And this includes also root datasets, which come in this format that is known as T3. It turns out that our data frame is your best friend when you just want to save stuff, when you want to save T3 into a file. Because there's one simple function that you can call. It's called snapshot. And it will store a T3 properly formatted into a T file, given the parameters that you pass to the function. So you can see it in this example here at the end of the cell. The parameters are self-explanatory. You have the name of the tree, the name of the data set that you want to store, the name of the file that you want to store the data set in, and then you can also make a selection of columns. In fact, in this example, we are taking the usual file from our data directory. We are creating a new column called C, and then we are saving it together with columns A and B. So you see that we have this list of columns, and then you can pass the list of columns as the third argument. And if we execute it, okay, we will see in the next cell that there is an actual file on disk with the correct name, and that it contains the T3 that we expected with the columns that we expected. So in particular, you see that this file has a T3 object, that its name is out3, the same name as we chose, and then there's a list of columns stored inside of the tree, A, B, and C. If you go back to the previous example, here, and you just also write vec1 from the name of the columns of before. Even a better example than this is showing you the fact that by default, this snapshot operation doesn't need this list of column names. And if you do not provide the list of column names, it will just store all the columns that are available to the data frame up to that point. So I can just repeat this cell and then go here. And then if I rerun the cell now, it will show all the columns, C, B, A, vec2, and vec1. So all of the columns that were available before, they're now available in the tree, because by default, that's what the snapshot does. And finally, we have, maybe you have not noticed it automatically, but this snapshot operation does not only store on disk, but also returns something. So there's a return variable up here. And the return variable can actually be used again, and it's just another RDataFrame object. So you can, for example, display its contents because it's available in memory of the computer as another RDataFrame object, kind of detached from the previous one. So you can restart your analysis and do other kinds of operations and manipulations with this. Some other topic is about, again, about the selection processes. This is a recurrent theme in high energy physics, of course, and the concept of cut flow reports. So sometimes you want to get a nice representation of how your filters affect the data set that you're manipulating. So the filter efficiency, depending on the columns, the branches, and which particle properties you're observing with the selections. In RDataFrame, you have this report operation that gathers all the information from the filter calls that you have applied to your data set, and then prints out this report if you ask it to after the event loop, after the computation loop is run. So in this case, I am taking a new file. Note as just something that is good to know, that this file doesn't even belong to the local disk, the local file system, but I'm actually passing it as a URL. This is very typical in our field. We have large data sets, and they are very, very frequently stored outside of your laptop, outside of your machine that you're running on. So we have the ability to read them from the remote location that they're stored at. And here I'm opening an RDataFrame reading data from this particular file. I have two filters on lepton properties, and I give them names. So a cut on the eta, a cut on the phi. And then the report operation down here at the bottom will tell me how many events passed the filter, how many events were present before the filter, and then just as a summary, report the efficiency of every filter and the cumulative efficiency of all the filters so far. Okay. All right. Clearly, we have already seen in previous notebooks that root is this package that lets you use Python and C++ together. RDataFrame is no difference there. And the way that you've seen, for example, Jonas in the beginning reporting on how you can use C++ libraries, define your custom functions, and use them from the Python side is the same in RDataFrame. Under the hood, it calls this C++ interpreter, which is called Cling, to use the C++ functions that you've defined. This function is a very simple one that takes a number and changes its type in this case. And I'm calling it sfloat. So it's a function that does a cast in the end. And then we can, okay, this is another function that squares a floating point value. And now we can use the functions in our data frame quite simply. You can either use them with this string syntax, as we have seen so far. You can also use them with the other syntax that we showed before, that they become part of the root module. So you have root dot function that you just defined. And this is how it's working in action. So after the definition of the new values, of the new columns, we can just plot them, for example, in a graph. And the graph will be shown using the values from the R data frame. So this is all bread and butter stuff for R data frame analysis. You will mostly see this in some frameworks that are already available in some experiment groups. And they use the libraries and the functions that are defined in the framework itself. Often they're also defined in C++. They use them in our data frame in this way, even if the user side of the framework is written in Python. And finally, as a final mention, our data frame and clearly root in general is a very performance-oriented software. In particular, all the nice features of lazy execution and booking all your operations up front that we were discussing earlier, they come in handy, especially when you want to introduce parallelism in your application. So nowadays, every laptop has at least 4 cores practically, or at least 4 threads. But most often you will see machines with upwards of hundreds of cores. And clearly, it's very nice if you could actually make use of those resources. And our data frame lets you do this quite simply. You just have to write one line of code at the beginning of your application. The line of code is as follows. Okay, in this case, I'm just showing you the baseline example by taking yet another file, opening an R data frame with it, and then summing the values of one column. Takes some time. And then in the next cell, I will do the same, but pay attention to this first line. You call root enable implicit empty, and then everything else will run using the maximum amount of cores available on the machine. I will run the cell now. It's quite probable that it will run as slow or even slower than the previous cell, for a simple reason. The reason is that this is not a powerful machine, but it's a shared instance with just 2 cores. And the data set is a data set stored remotely. So it's not a performance-oriented scenario here. But if you might happen to have a performance-oriented scenario and you have a powerful machine at hand, then just know that with one line of code, you go from using 1 core to 128 cores on your machine. So it could be quite useful to keep in mind. This is a simple, very simple example of an analysis with open data from CMS. And the goal of the analysis is to plot the invariant mass of the dimuon system. So for the physicists in the audience, you know what we are about to do. And let's try to do this together, right? Let me kickstart the notebook for you or with you, and then I will let you attempt writing the important bits of the analysis. So the data set in question, as I said, is an open data file from CMS stored on a remote location in the CERN data center. In this table, we are just showing the columns and the data types that you have inside of the data set, right? So there are 6 columns. Most of them are vectors, are collections, and only one represents the number of muons in the particular event that you're processing. First cell is easy. We are just giving you the name of the tree and the name of the file or the path to the remote file so that our data frame can process it. And then the rest is where the analysis really is. The first cell here is just a detail. This data set has 61 million events. Probably they would be too many if we try to run them right now all together. It would take a bit of time. So I'm doing this. I'm just showing you how to select with our data frame the first 1 million events. You have this simple df.range operation. So write it in that notebook cell, and then our data frame will only process the first 1 million events from the dataset so that you can see the results a bit quicker. It will the final histogram maybe will not be as clear as this. There will be less statistics, but it will still show you roughly the same distribution. Okay, and then we have 2 parts of the analysis. One is the filtering of the events that are, interesting for getting the invariant mass. And the other one is creating the invariant mass. In this case, because there is already a very simple function ready-made for you and available in root, we just wrote it already for you, so you don't have to care about that. But the filters are there for you to fill in. So you have to understand what to write in the cuts, or you can think about it, and then you can plot the histogram afterwards. There is also a request for booking a report of the operations. So it would be nice if you didn't only see the final histogram, but also the efficiencies of the different cuts. Let's take 5 minutes, and then let's do this together afterwards. We stopped at this cell, right? We are just selecting the first million events so that whenever we try to plot the histogram, actually it won't take too long. Okay, and this was the next cell. So the text above the cell tells you already the kind of selection criteria that you want to apply. And then there are two filters that have already in them the hint as to what you have to do. The part that is missing is the expression. So for the expression, the first filter is the one where the events should have exactly 2 muons. How do we write the expression here? Yes?
mu equal to.
All right, and mu1 equal to. This makes sense, right? Because if we go back to this table that shows the dataset schema, we know that the n muon column is the column that represents the number of muons in the particular event. So for every event, if we check whether n muon is equal to, then we know that we have exactly 2 muons. Okay. Next filter, next selection.
Charge equal to 0.
Muon charge equal 0. This is what you wrote? Or just to make sure I'm understanding.
Yeah.
Okay. So muon charge equal 0. Let's try to think about this. We go back to the table. And we see that muon charge is an array of type int. The dimension of the array is n muon. And it says charge of the muons stored as an array of size n muon, either -1 or 1. Clearly, this is the charge. Okay, if we go back to the selection, here what we are doing is tell me if the array is equal 0. But from the perspective of the array, we don't know whether, what will this operation do? Will it do every element is equal to 0, or are you expecting this to do something like tell me if the size of the array is equal to 0? What's your expected outcome from the operation? So the thing that the assignment says here is that the muons in this event should have opposite charge. So what I am missing from this selection here is something that tells me that 2 elements of the array should be opposite, no? Because we are looking for the muons that have opposite charge. Did anybody try anything else? Maybe down there? Yes? Okay. So the sum over the elements of the array, clearly. What does this mean? Let's try to look at it. We have an array, and we know that the array has size 2, because the filter that we did before is only give me those events that have 2 muons. So the muon charge will be an array of size 2. Okay. We know that the array is an array of integers, and it's either -1 or 1. Interesting. So if we sum 2 elements and the sum is 0, then we derive that -1 plus 1 is 0. Okay, this is an interesting approach. How did you write this? With a for loop, with some operation to accumulate. Okay. Okay. So what we could do is writing it this way. So we could do int sum, right? And we can do for auto e0 e less than muon charge dot size e plus plus. We do sum plus equal mu1 charge of type, index I, and then we return sum equal 0. This is roughly speaking the implementation of what you described. So we sum the elements of the array into an external variable, and then what we return, which is the important part, maybe let's write this like so. If we write, come on, okay. If we write it this way, it will be a bit clearer probably. So we have the for loop, and then what we return is the important part, right? We have a return statement, and we say in the return statement, tell me whether the sum is equal to 0. Okay, interesting. Were there any other attempts at this? Okay, so this could be a second approach. We have it here. We could do mu1 charge of 0, the first element, is equals to minus 1 times mu1 charge of index 1. Okay, yes, this is also another approach. Let's try, I don't know, is there a third way? Let's try with the first, just for the sake of going on with the exercise. Good. Okay, this is the other part of the analysis, but in this case, root already offers a nice invariant mass function, so you don't have to code it yourself. So there was nothing to do here. And this is the final bit where we are creating the histogram, and the exercise was asking you to put the histogram parameters in the right order. This is just a check to see if after a couple of hours seeing histograms over and over, you remember the order of the parameters. What's the first one?
Title and then
Right. Okay. So name, title, and bins, and then the range of the x-axis. Okay. Then the request for booking a report should be simple. What do we write here? We saw this in the notebook just before the exercise. Maybe I went a bit too fast on it. So the title kind of tells you, right? The title of the slide. There's this functionality in RDF, which we will see used here exactly, called report. So whenever you want to know how your filters were applied to the data set, you can ask to the data frame object. What did I do here? Right. You can ask to the data frame object to report what happened during the filters. So was just a simple check here. Okay, we booked it. And finally, we can actually start the analysis, right? There is some customization of the layout of the histogram done for you so that when you go and match it with the link that we provided, it kind of looks the same. So let's start the cell. And let's see if everything runs without problems. Okay, nice. So everything seems to run without problems. Final check. Let's see how the histogram looks. Okay, pretty cool, no? It's shows the same distribution as the open data result. Clearly, if you go look at the other picture, you will see it a bit more defined, whereas here it's a bit wiggly, but clearly that's because we only restricted ourselves to the first million events. And then just to end the exercise, you can ask the report to print the values obtained from the two filters. So you have the first filter on the events that have 2 muons. From 1 million, we go down to almost 500,000. And then the second filter where we check the muons with opposite charge, we go from that number to 371,000. And that's what you actually see in the output from this cell. So today we covered a number of topics. We had a nice introduction into what root allows you to do, specifically everything that has to deal with the parts of the workflow that are more related with the analysis. So creating histograms, important statistics from your data set, how to run fitting on your statistics, creating a file, opening a file, writing stuff into the file, and then finally a big excursion into our data frame analysis and how it can actually be practically useful if you have root files and you want to process them. In this other slide, we leave you the usual list of resources. Feel free to reach out to us in any way or shape. You can see we have a forum, we have websites and documentation, and you can find us if you have any problems also on GitHub. You can open issues. Cool. The rest of the slides is just extra material for you for self-study in case you would like to go a bit deeper into root. And with that said, thanks again for joining us today from me and the rest of the team. And yeah, have a nice rest of your summer studentship at CERN.